In our last section, we learned how to use a geometric series to develop a power series. And in section 9.7, we looked at Taylor and Maclaurin polynomials. Now we're going to look at Taylor and Maclaurin series, as well as a new kind of series called a binomial series. We'll use these to develop our power series. Okay, let's look first at the format of a convergent power series. Okay, so if F is represented by the power series f of x equals the sum of a sub n times x minus c to the n power for all x in the interval I, which has to contain the c from up here, then a sub n is equal to the nth derivative of f of c divided by n factorial and f of x is equal to f of c plus the first derivative of f of c times x minus c plus the second derivative of f of c times x minus c squared over 2 factorial, continuing up to the nth derivative of f of c times x minus c to the nth power divided by n factorial. Okay, so this is our format for a convergent power series. And let's write this format up here again. And we'll just expand it a little bit again. Okay, so if we have this, this is called the Taylor power series. And you might say, well, that's just the Taylor polynomial. The difference is the Taylor polynomial has an end. We stop it at some point. We choose to stop it, make it a third degree or a fourth degree polynomial. The Taylor series is an infinite series, so it just continues. And just like with a polynomial, if I take a Taylor series and let c equal to 0, then that gives me a Maclaurin series. So it works just like it did for the polynomials, Taylor-Maclaurin polynomials. Okay, let's do some problems. Okay, I want to find a power series where f of x equals sine of x. Okay, and I'm going to form a Maclaurin series. So this will be a 0 over n factorial times x to the n power. So I'm going to have f of 0 plus f prime of 0 times x plus the second derivative over 2 factorial times x squared, and so on. So first we want to take some derivatives of f. Let's start off with f of x equals sine x. That was my original. The first derivative is cosine x. The second derivative is negative sine x. And the third derivative is negative cosine x. And after the third derivative, this just repeats itself again. The derivative of negative cosine x is sine x. So f of x and the fourth derivative are the same thing. So let's put in some values. F of 0 is going to be sine of 0, so 0. F prime of 0, so cosine of 0 is 1. Double prime is going to give me 0 again. And the third derivative gives me negative 1. And then I just keep repeating that pattern. Okay, so that gives us a power series. And rather than write this all out again, I'm just going to replace things. F of 0 is 0. F prime of 0 is 1, so this is going to be plus 1x. And then the next one, I'm going to have 0 over 2 factorial times x squared. Well, that 0 in the numerator is going to cancel that term out, so I don't really even need it. Now I'm going to have negative x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Because every other derivative is 0, I'm only going to have odd powers in my series. And then I can sum this up. Negative 1 to the n power times x to the 2n plus 1. That's how we get every other power, by using 2n divided by 2n plus 1 factorial. Okay, we can use the ratio test on this, and the ratio test will show us that this series converges for all values of x. So we're just going to say it converges, and that's all we need to do for that one. Before we go on, I'd like to go through the theorem 923 that talks about the convergence of a Taylor series. And it looks like this. If the limit is n goes to infinity of r sub n, where r sub n is our remainder, if that limit is 0, for all x in the interval, can't spell interval, interval I, then the Taylor series converges and equals f of x, where f of x is equal to the summation of the nth derivative of f of c over n factorial times x minus c to the nth power. Okay, and if you're interested, the proof for this theorem is in your textbook. So we're going to take this same function again, f of x equals sine x, and we want to show that the Maclaurin series for this function converges. So looking at the result we had in example 1, we've got sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial all the way up to negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. We want to say that this is true for all values of x. So we want to say f of the n plus 1 of x is equal to positive or negative sine x, or we could say that f to the n plus 1 of x is equal to positive or negative cosine x. Okay, those are our two possibilities. And since sine x and cosine x are both always less than 1, we could say that the absolute value of f to the n plus 1 derivative of z is always going to be less than or equal to 1 for every real number z. So because this is true, we can apply Taylor's theorem to conclude that the remainder is greater than or equal to 0, which is equal to absolute value of the n plus 1th derivative of z over n plus 1 factorial times x to the n plus 1, close the absolute value, which has got to be less than absolute value of x to the n plus 1 over n plus 1 factorial. Okay, and we talked about how fast the convergence goes for exponential and factorial sequences. So for a fixed x, the limit as n goes to infinity of the absolute value of x to the n plus 1 over x plus 1, n plus 1 factorial is equal to 0. Okay, and then we're going to go back to the squeeze theorem, which tells us that for all x, r sub n of x goes to 0 as n goes to infinity. Okay, so that tells us that this Maclaurin series is going to converge for all values of x. Before we go on, let's go through some basic steps that we need to take to find a Taylor series. First of all, we're going to take our function f and differentiate with respect to x several times and then evaluate at c. And when we get those numbers, we're going to look for a pattern in the numbers. And then we're going to use whatever sequence we got from that to form a Taylor coefficient. A sub n equals f, the nth derivative of f of c divided by n factorial. And then determine the interval of convergence. And then when we're inside the interval of convergence, determine if the series converges. Okay, let's go through those steps one at a time in these examples. So this time we're going to use a composite function, sine of x squared. Okay, so to find the coefficients, we have to do some derivatives. So the first derivative of this is equal to 2x cosine x squared. And the second derivative is equal to negative 4x squared sine x squared plus 2 cosine x squared. Okay, so we've only done 2 derivatives. And our guideline says do several derivatives. These are just going to get more and more and more complicated. So maybe this is not the route we want to go. Okay, there is something else we can do. Okay, we're going to look at the Maclaurin series. No, that's not how it's spelled. We're going to go back and look at that Maclaurin series for sine of x. Okay, we're going to call this g of x is equal to 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And we're going to say that since sine of x squared is equal to g of x squared, because g of x, this is our series for sine. So I'm going to just substitute x squared in this series. Okay, and this should have been x, not 1. That's x. So I'm going to take all of these x's and put in x squared. So I'm going to have now x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Okay, and this can be my series. Now we're going to look at a different kind of series called a binomial series. If I have a function f of x equals 1 plus x to the k power, I'm going to say k is not a positive integer. And also that k is not 0. Let's look at some derivatives. Okay, this is f of x. F prime of x is going to equal k times 1 plus x to the k minus 1 power course, f double prime of x is going to equal k minus 1 times k times 1 plus x to the k minus 2 power. And let's do one more. Third derivative of x is equal to k minus 2 times k minus 1 times k times 1 plus x to the k minus 3 power. Okay, so let's get some numerical values here. Okay, so at f of 0, if x is 0, this is 1 to the k power, and it's just 1. First derivative at 0, again, if this is 0, it's just going to be k. The second derivative is going to be k minus 1 times k. And the third derivative is going to be k times k minus 1 times k minus 2. Okay, and we can keep going however many derivatives we need. But this gives us a series 1 plus kx plus k times k minus 1 x squared over 2 plus, we keep going with the pattern until we get to k times k minus 1, and keep multiplying until we get to k minus n plus 1 times x to the nth power over n factorial. By using the ratio test, we can see that the ratio of convergence r is equal to 1. So the series converges on the interval from -1 to +1. Okay, and just notice that even though we say it converges, it doesn't necessarily converge to this. Okay, it might converge to something else. So don't assume that it converges to this value when you're working these problems. Okay, now we're going to find a binomial series, and we're going to up the difficulty a little bit. F of x is equal to the cube root of 1 plus x. That's our function. So we're going to use a binomial series. I've got 1 plus x to the k power is equal to 1 plus kx plus k times k minus 1 x squared over 2 factorial k times k minus 1 times k minus 2 x cubed over 3 factorial, and so on. And we're going to let k equal cube root. So k is equal to 1/3. And we're going to say 1 plus x to the 1/3 power is equal to 1 plus 1/3 of x minus 2x squared over 3 squared times 2 factorial plus 2 times 5x cubed over 3 cubed times 3 factorial. And then we're going to need to subtract the next one. And this is going to be 2 times 5 times 8 x to the 4th over 3 to the 4th times 4 factorial, and so on. So this is our series. And you can verify this to compare our results from this example. Let's put both of the equations in the calculator and look at their graphs. I'm going to start up here with y1 and use that for my original function, which is 1 plus x, close the parentheses, and we're going to raise that to the 1/3 power. Make sure that you hit the right arrow when you're done with your exponent, or it'll just keep everything in the exponent. Now we'll go down to y2 and put in our series. Got 1 plus, I like to put each term in parentheses, helps to avoid mistakes. So I've got x divided by 3, close the parentheses, and I'm going to subtract x squared. No, I didn't do my parentheses. I can go back using the left arrow, and I'll do insert and put that parentheses in there, and then use the right arrow to go back to where I was. I want x squared divided by 9, close the parentheses, add new parentheses, 5 times x raised to the 3rd power, and use the right arrow to get out of the exponent, and divide by 81. And then our last term will be minus 10 times x raised to the 4th power divided by 243, and close the parentheses. When I've got both my equations in, I come up here to graph, and I've set my window already so that x goes just from -2 to +2, and y goes from -1 to +2. So this looks just like the picture in the textbook. And you can see between about -1, a little bit more, up to just past +1. This is a very good approximation of the function that we wanted. In your textbook, on page 674, there's a table of series along with their intervals of convergence that you can use to help make other series. So let's look at this example. I got f of x equals the cosine of the square root of x. Okay, and I know that the power series for cosine x is 1 minus x squared over 2 plus x to the 4th over 4 minus x to the 6th over 4 factorial, and this is 6 factorial, plus x to the 8th over 8 factorial, and so on. So we're going to replace the x, we're going to put in the square root of x instead. So now we have cosine of the square root of x is equal to 1 minus square root of x squared is just going to give me x over 2 plus x squared over 4 factorial minus x cubed over 6 factorial plus x to the 4th over 8 factorial. Okay, and this series will converge for all values of x in the domain of the function, that is for x greater than or equal to 0.